So, hello everyone. We have had some requests to do some certain questions from Module 5. Most of us are still finishing. I know a few of us have already moved on to Module 6. But Module 5 is notoriously known as the module that takes us the most time and does tend to degenerate into being quite difficult. So the first question that I grabbed, and I can tell you it is from Module 5, Lesson 4. But you know, this is the exact question from the quiz. I think I'm just not wanting to do the exact question. Why not I do sine 15? And then just gives you the chance to go and do cosine 15. I think it's good, you know, for the extra practice for you. Now, you guys have seen exact value questions before, quite a lot of them. The issue comes up with exact value questions. What process do I use, right? Is it going to be just drawing it on the grid? Is it going to be using the unit circle? What is it going to be? And sometimes it's easy to decide and sometimes it's not so easy to decide. When we look at this angle here, 15 degrees, it is an angle we know nothing about, right? 15 degrees is not one that's got some nice points on our unit circle. It's a kind of a rogue angle. But if we can come up with two angles that add to 15 or subtract to 15, we can use the addition and subtraction formulas. So if you guys wanted to grab out your formula sheet to have handy, and if you don't, I can write the formula down that you're going to want to excuse me, spy. But down on the right-hand side, not right at the bottom, I would say kind of 2/3 of the way down, you're going to see a bunch of formulas and they're going to say sine of A plus B, sine of A minus B. Well, it's alpha and beta, but I'm going to call them A and B. And cos A plus B, cos A minus B, tan, etc. You see them there. We're going to try to apply one of those. Okay, so before we decide which one is going to work for us, let's try to figure out what angles we would want to be using here. So two angles we want to be able to add or subtract to 15. If you think about the angles we know lots about 30, we know lots about 60, we know lots about 45. That's not in any kind of order. And any reference or any angles to do with these having reference angles. We also could deal with anything on the axes, like actually I could take the 9 out. So 0 and 90 and 180 and 270, 360. All of those are nice and easy to find answers for. 15, not so much. But 15 degrees is 45 degrees, take away 30 degrees. Or you could do 60, take away 45. Truly doesn't matter. You're going to come up with the same answer. Okay, so we're going to rewrite our question. I'll go back to my black pen. That sine of 15 degrees, we're going to try to apply sine of 45, take away 30. Now, if you look down your formula sheet, I'll put the formula up here in red. You will, hopefully you'll identify it before I throw it up here. So it says, and I'm just changing the alpha and beta to A and B. So it says sine of A minus B is equal to the sine of A cos of B minus the cos of A sine of B. I'm going to go back and double check. I don't commit these beautifully to memory. As I've told you a number of times, I only can put so much in my brain, but I think I've got it right. Sine cos minus cosine. Sine cos minus cosine. Yeah, okay, there's our formula. So because we know tons about 45 and tons about 30, this is going to turn into not as hard a question as we might have suspected. And I don't know. I don't want to say that I'm in your mind and you might have thought it was hard. But it's just going to be a process of substituting the numbers. So sine of 45, cos of 30, take away cos of 45, sine of 30. Special triangles can then get you your answers. If you've taken the time to memorize your unit circle, you can get your answers from there, wherever you want to get your answers from. So sine of 45, I'm not doing it with rationalized denominators. We can do that at the end if we want. It's 1 over root 2. Cos of 30 is root 3 over 2. Cos of 45 is the same as sinus 45, 1 over root 2. and sine of 30 is 1 over 2. So those are just either straight read off the unit circle or by the special triangles. I hope I can just go that quickly. You guys can give me puzzle looks if I'm going too fast. I'm trying to watch you on my other screen over here. Okay, then we just multiply the numerators. So we get root 3 over 2 root 2. Take away 1 over 2 root 2. We can then finish because we've got a common denominator of root 3 take away 1 over 2 root 2. Now, I know that I've had a couple conversations with a few of you about rationalizing the denominator. Depending on if you're surfing around the net and you're Googling and you're watching some Khan Academy or whatever you're doing to fill out, you know, if you want some extra help, you might hear lots of people say this is a bad answer. And I kind of agree that we shouldn't have the root 2 on the bottom. They don't really seem to be all that worried at the diploma level, regardless of whether we're going to have one or not, which is up for grabs. But I'll just show you how you would change it so it's not got an irrational number in the denominator. We just multiply the top and the bottom by whatever the radical is on the bottom. So this is how rationalizing would work. And then our answer, we can multiply root 3 by root 2 and get root 6. Take away root 2 over 2 times 2, because root 2 times root 2 is just 2. And then we could write our answer as root 6 minus root 2 all over 4. So if you're wondering what I will accept for answers, because the diploma exam people seem to think this is okay, like there's only so many things they want to be hardcore about. They've sort of dropped that a bit, which is fine, but I also will take this answer. Okay, both of them are fine. Maybe the second one is somewhat a little bit better because it has a rational number in the bottom. Okay. Okay, so our second question is another equation with identities in it. So it's one of those crossover things that adds another layer of complexity to the question when we have that. So we got sine x plus 4 cosecant x plus 5 equals 0. The given domain is between 0 and 2 pi. We can talk about the general solution at the end to kind of work that into, in case anyone's worried about general solutions. Add conversation will work nicely here. So to start with, anyone want to suggest in private what we would start with? Or if you're okay being on the recording with your audio, you can come on the audio and just tell me what you might suggest. It's your comfort level is, it's up to you. What would we do here? Give me a few suggestions.
Can you repeat what the question was?
Oh, absolutely. Can you guys see it on the whiteboard?
Like,
you can
yeah.
see the question? Okay, so the question is, what do you think we should do first, really, and make it easy? We need to try to not have 2 trig ratios. So is there any way we can get to the point where we just have 1 trig ratio that we're dealing with? Is there a substitution that we could do is really what we're looking for? Kind of keep it in the back of our mind too, that we'd like to do things with sine and cosine most of the time, not all of the time, but most of the time. Yeah, that I think is a suggestion. So I got the suggestion, take cosecant x out and put 1 over sine x. And I think that's going to be the suggestion that gets us moving in this. So we'll have sine x plus 4 over sine x is how that would look, plus 5 equals to 0. I'm going to try to get kind of lined up so it looks like I'm actually looking at you. It's kind of weird to not be. Okay. So now we want to try to get rid of the denominator sine x. Do you guys remember a question in assignment 4 that asked you what's wrong with this solution? And the student had gone through and divided by sine x, and dividing by sine x, what they did is they lost a whole series of answers. So you can't divide by something, but you can multiply by something. You're not breaking any rules if we multiply by something. So let's go here and multiply by sine x. And that's going to then make the first term sine squared x, make the fourth term just 4 because the sine x's are going to cancel. And then we're going to get 5 sine x and then equal to 0 like that. Okay. Now order is not really great. We've got our number stuck in the middle. So we would want to reorganize it like this. And then that's a pretty easy factoring question. If you don't like the sine x in there when you're doing the factoring, put a letter A in there and then factor. I'll pause the recording and I'll shut my audio off for a moment. I'll give you guys a chance to kind of mess around with it. Okay, I'll resume recording. Had a question. I think I want to do one more step in here just to be clear as to what happened, because I think I lost a few people. So right up here, what we did was we recognized, if I just go over here kind of with what we used, that cosecant x is equal to 1 over sine x. And so perhaps I should have added in here, because I don't want to go too fast and lose you, that in replacement of cosecant x, I put 1 over sine x. And then I just multiply those together to get 4 over sine x, because the 4 times the 1 and then the sine x is in the bottom. So hopefully that helps a little bit there. Okay, so we're factoring. So we're trying to find a product of 4 and a sum of 5. So I would leave the sine x in just because it's actually quite decent factoring. Sometimes if it's ugly, I take it out. So we get sine x plus 4 and sine x plus 1 equals 0. And so then we get sine x equals -4. There's no solution here, so no answers here. And we get sine x equals -1. So then now it depends on how you want to find sine x equal to -1. You can use your calculator if you want to go second function sine. My thought is I always think, okay, as soon as I get 0 minus 1, it's got to be something to do with the unit circle on these axes system. So I quickly jot down 1, 0, 0, 1, minus 1, 0, and 0 minus 1. Excuse me. And then the second coordinate on the unit circle is sine, which is this dude down here, and that's the only one. And because we're in radians, then we're going to write that x is 3 pi over 2. And there's our final answer. And that's our only answer. Okay. For our given domain that we're given here. Now, if we're asked to do a part B, and let's say, and because they'll do this, they'll say, do the same question, but now do it over the real numbers. Okay, and that just is another way of saying do the general solution. All we do, general solutions sound complicated, but they're actually super, super easy. It just means we want to get to our answer and then add a rotation as many times as we want. So the answer here for general solution is 3 pi over 2 plus 2 pi n, n being an integer. And so that means we're going to add 2 pi lots of times or subtract 2 pi lots of times, and we're just always going to end at the negative y axis. So that's how you do general solution. They really aren't, they sound complicated, but they're not as complicated as actually the math to get there. Okay, so I'll catch the recording up to where we are. So here's our next question. We're given some sort of identity expression. It's not really an identity equation. And we're asked to figure out something equivalent to it. And so I did have a little mention off the recording that we're not exactly sure where to end. So we do definitely have to have it in a multiple choice type scenario. So we see we're going to tangent. I guess we could word this to say sine 4 theta over 1 plus cos 4 theta in terms of tan is. I guess that's how they could do it so that it wasn't a multiple choice. So does anyone have a suggestion they'd like to give me as to what we could try here? We really don't have a lot of opportunities to have an angle that's a 4. We sometimes have sine 2 theta and cos 2 theta, but we don't often have sine 4 theta. Anyone have a suggestion as to where we could pick up on this one? And if you want to come on the audio again, that's fabulous. You just will be part of the recording if you want to use your voice. Anyone? I can jump in here. To me, this screams addition, subtraction formulas for sure. So again, on your formula sheet down part way on the formula sheet where you have sine of a plus b and cos of a plus b, that's where I think I'm going to go with this one. And that is one of the issues is, and what are you going to try? And sometimes it is just a try. I'll put the formulas over on the side here for us to ponder. So it's sine of a plus b and cos of a plus b that we're going to go after. And the formulas are sine of a plus b, sine cos plus cosine. So sine a cos b plus cos a sine b. That's the sine a plus b one. And cos a plus b is cos cos minus sine sine. So cos a cos b minus sine a sine b. Okay, so those are our formulas. I'm looking at these answers. I notice that none of our answers have a 4 in them, so I'm going to start with these addition and subtraction formulas and see where what road that leads us down. Okay, so we're going to have the top. I think I'll do it separately. So let's just look at what we would do with sine 4 theta. I could rewrite it as sine of 2 theta plus 2 theta, because 2 plus 2 is 4. So then our formula would be sine 2 theta cos 2 theta plus cos 2 theta sine 2 theta. Anyone help me put that together? Can we simplify that a little further before we go and look at the denominator? Sine 2 theta cos 2 theta plus cos 2 theta sine 2 theta. Something we can do there. I'll give you a second to think about it. I don't mind carrying on, but I like to have some pauses so the students that are here live can have a few minutes to try on their own. Josh, your dad want to do some work too? Sorry, I guess
well, it's his office, so he's kind of here.
Who's this? Hi, Dad. You're on the recording. How are you doing?
Sorry, how are you?
I'm good, thank you. Okay, so when we're looking at this, do you guys notice that if I do a little reorganization, we actually have identical terms here? So if I do sine 2 theta cos 2 theta and just leave that, there's no reason that I can't write this as sine 2 theta cos 2 theta back here, just reorganizing, right? Cos times sine and sine times cos, same thing. Like I just reorganize it. So this I could rewrite as 2 sine 2 theta cos 2 theta. There's 2 identical terms there. All right. I don't see too many deer in the headlight looks. Hopefully I got you guys with me. It gets complicated. Not an easy course that you're in. Now let's look at the bottom. So 1 plus cos of 4 theta, kind of going to go the same way. You got 1 plus cos and then 2 theta plus 2 theta. So we just have to carry this 1 plus along. So it's going to be cos 2 theta cos 2 theta minus sine 2 theta sine 2 theta. Yeah, that's not particularly lovely at this point. Anyone have any suggestions about what we might do there, or Anyone have anything? We'll just keep powering through. I'll give you a second. Okay, so let's have a look at this. If we put this back together, like I always like to just kind of pause and go, did I take the right direction? Because you never quite know. I don't see anything here that's going to combine and cancel. That's my worry, right? Because I've got like a cos 2 theta. I don't have anything that's similar top and bottom. So I don't know if I like this. So we might have to regroup and try something different. Can someone give me another suggestion to try? Can you look at your formula sheet? Hopefully you have it there. Is there a formula a different formula that we possibly could try? Look a little bit further below the addition and subtraction formulas. Do you notice that there are 3 different formulas down there? There's cos 2a from alpha equals cos squared alpha minus sine squared alpha. There's cos 2 alpha equals 2 cos squared alpha minus 1. And there's cos 2 alpha equals 1 minus sine squared alpha. Oh, there's lots of different options there to try. We could try one of those. Anyone want to tell me which? Well, maybe I don't want to. Maybe we don't want to try all 4 of them. Maybe I'll tell you which one might be helpful for us. So let's try the second one that says 2 cos squared alpha minus 1. So I'm going to write that one in red again on the top of our board. And we'll go see if that one might lead us down the road to success, because we need to try to figure out what's going to cancel top to bottom. You don't always get it right the first time. Okay. Okay. So the next formula we're going to try here is the formula cos 2, I'm going to just call it A, is 2 cos squared A minus 1. Let's try that. See if I think that's the one that's going to lead us down to success. I'm just going to look at my help document and make sure that we don't do too many things. Got that. Here's the formula. Yep. Okay. So let's try this. So in here, we don't have 2 theta. We have 4 theta. So we're going to have 1 plus cos of 2 times 2a, right? Because we're trying to make it be in this format. So it's a double angle identity, and we're doubling it again. We're doubling the angle inside. So what do we got here? Minus 1. Oops, I forgot my 1 at the beginning. Oh goodness, here, let me just do a little bit of erasing here. Erase 1 plus. Have a look at that. Make sure I wrote that part down correctly. Okay, that looks all right. Everyone see how that worked? It's a double, like, so our angle now is 4 theta. I'm changing it. Oh, I guess I should go back to thetas, not A's. I'll go and put the thetas in here. Okay, like that. So we put basically 2 theta in there and 2 theta in there is what we did. Okay, so there's that attempt. So now we're going to go back to our original expression, which is this divided by this. So let me move my slide up. And so I'll just rewrite the original question. So you have it, sine of 4 theta over 1 plus cos of 4 theta equals 2 sine 2 theta cos 2 theta over 1 plus 2 cos squared 2 theta minus 1. Now, lucky enough, we do have some canceling that happens here. I'll do it in a different color. This minus 1, this plus 1 cancel. And so we get 2 sine 2 theta cos 2 theta over 2 cos squared 2 theta. Beautiful. So these 2 cancel. Again, I'll use a different color. These cancel. And this squared cancels with that cosine. So then we end up getting sine of 2 theta over cosine of 2 theta. Sine over cosine is tangent. So then we can reduce it to that. And so the option is going to be B in the order that we have it, this guy here. Okay, now that's a pretty tough question. No way around it. You're not going to see a ton of these on a test. You're likely not going to see one quite that hard. On an assignment, yeah, and I think it's up for grabs. But that's a pretty in-depth question for 1 mark on a test, right? Because that's just the way it goes. So don't think you'd see that one on a test, but it certainly does stretch us. Now I'm just going to turn the recording off again for a moment. Okay, our last question for today comes from the textbook, but I've kind of tried to summarize it here on the board. It's page 323, number 14. And so in the textbook, it says, consider this equation, sine of 2x equals tan of 2x over 1 plus tan squared x. Part A says, verify the equation for pi over 4. But then it also says, does this mean that the equation is an identity? And I kind of summarized it to say, does this mean you have proven it as an identity? Like, so we'll think about that. And then it asked us to talk about non-permissible values, and then it asks us to prove it for all x. There's quite a lot of math in this question for sure. Now, verifications, when you are asked to verify, especially if you're on an assignment or anything, something long answer, when they ask you to verify for pi over 4, you have to keep exact values. Like if you're not sure about exact values, just pretend it says exact values. So my expectation is going to be, we're not grabbing our calculator for any of this question at all. We are going to power through. Okay. Now, if we're going to verify for pi over 4, verification, remember I set this up for you before that we want to use the line down the middle. We still want to do that. Even though this is only a numerical proof, I still want to see it. I won't get too worked up if you don't do it for just a number, but okay. So we're doing sine of 2 pi over 4 because x is pi over 4, and then 2 tan pi over 4 all over 1 plus tan squared of pi over 4. Okay. So this is actually the sine of pi over 2, right? Because 2 pi over 4 is pi over 2. Sine of pi over 2, use the unit circle, think about the sine, the second coordinate of 90 degrees. Basically, pi over 2 is 90 degrees. And so you're going to have 0. So this is going to be 0. Sine of pi over 2 is 0. Again, if I did that in the air, but if you need it shown here, the 4 points are 1 and 0. Is 0 and whoops, did I pick the right one? I picked the wrong one. Of course I knew it. See, I can't do anything in the air. And then 0 and minus 1. So take the second coordinate, your answer is 1. Good thing I went back up there. Okay, now we got to do the other side, pi over 4. So pi over 4, again, I kind of work in degrees. You guys know that. So this is the 45, 45, 90 triangle. So tangent of pi over 4 is 1. Whoops, I can drop the word tangent now and just put the number 1 in there. And then this is over 1 plus 1 all squared. So we get 2 on top, 1 plus 1 on the bottom, 2 over 2 is 1. Then we can just kind of drag this 1 down here and say, good, it is correct. You get 1 equals 1. Now, does this mean you've proven it as an identity? No, what this means is we've proven that this works for pi over 4. It doesn't work for every single value because you notice someone asked me at the beginning to talk about tan graphs. This is a good spot to kind of pull it into this question. Tan graphs have non-permissible values. A tan graph, before we actually go to part B, just kind of as an aside here, let me just erase a few little things because I'm moving into what I had on the board. Hopefully you have a little vision of what a tan curve looks like. You may or may not, because we don't do it a ton, but there is the expectation. A tan, wow, that's supposed to be a straight line. So a tan graph looks like this. So it looks like a series, and they've got these asymptotes, right? That's what a tan graph looks like. So at all these asymptotes, it doesn't exist, okay? So we would not be able to say that just choosing pi over 4, which on our tan graph would be like right here, right? Pi over 4 and 1, it's be about there. Just proving that one point proves it for everything it doesn't. Okay, we have to do it more globally. Now, we're talking about non-permissible values. Let's go back over here. Second part was non-permissible values. When we look at non-permissible values, we have to look at denominators. We have to look for when the denominator is equal to 0 and then say we can't have that. So when we do tangent, basically you have to keep in mind, I'm just going to erase part C and then I'll put it back here just so I have a spot to do part B. This side doesn't lend us to any non-permissible values because there's no denominator. So good, we don't have to worry about that. But tangent, if we just look at 2 tan x, we have to evaluate that because that's 2 sine x over cos x. So really when you're doing tangent x, you are doing cosine x because it's the denominator of tangent x. So who knows, you just see this coming along. Who knows what the non-permissible value is here? Anyone want to say it or type it? What values of x are cosine 0? Anyone want to type that? No gumption. And I've asked for lots of you guys. You guys have been very involved. It's great. Okay, so cosine x, think about it. We're looking for when cosine x is 0. Cosine x, if you go up my little unit circle, is 0 at 90 degrees and every 180 degrees after it. Or set in radians, because we assume radians, it's at pi over 2 and every pi after that. So the non-permissible values for this are going to be, I don't really want them in red, sorry, are going to be pi over 2 plus pi and n is an integer. That's one of our sets of non-permissible values because that's when cosine would be 0. The second thing we have to look at is the bottom of the right-hand side. So we're looking for 1 plus tan squared x is equal to 0. You can do this a number of ways. I don't know, let's do it like this. Tan squared equals minus 1. Is there ever a time where tan squared can equal minus 1? Where does that happen? Does it happen? Can it happen? Is it a non-permissible value? Is it something that happens? You could try it on your calculator. So like, what do you think? Someone give me some insight here. Can this ever happen? Oop, I got someone. Yeah, no, because it's a square. So think about this. Very good. Absolutely excellent. If I asked you then to square root both sides of this equation, right, to get rid of the square, we can't square root -1. So there's no non-permissible values here. This is the only set of non-permissible values. Whew. I hate non-permissible values, but that wasn't so bad. Now we're supposed to verify. So now we actually have to prove it, basically is what they're asking us to do. So let's go and finish the question by doing an algebraic proof. So 2 tan x, oops, just a minute. I'm sorry, that's not the right-hand side, left-hand side. It's sine 2x on this side. And then we're supposed to prove that it equals 2 tan x over 1 plus tan squared x. Okay, set up the format. Again, it's up for grabs as to what we might want to do. The general rules are work on one side, change to sine and cos, do some factoring work. Again, I haven't done this question, so I'm at the wilds of it as just like you are. I would choose to work on the right side and change everything to sine and cos and see how that went. If it goes good, great. If it doesn't, well, I might have to backtrack. So I would start by going that this is tan is sine over cos. Now 1 plus tan squared, that rings a bell that is actually a trig ratio, like a formula. And so if you check your formula sheet, that's secant squared x, which is wonderful. Okay, so that's very good. So we can put that in there. Now, again, I think I'm continuing to change the sine and cos. So the numerator, I'm going to tuck the 2 up here. So it's going to be 2 sine x over cos x. And then my big division line, and secant squared is 1 over cosine squared. So I'm going to go 1 over cos squared. So now we're going to invert and multiply. We're going to get 2 sine x over cos x multiplied by cos squared x over 1. And the cos x will cancel the cos squared, and we get down to 2 sine x cos x. Now I'm just going to bring the other side. It says sine 2x. I'm going to bring it down here. Okay, now I don't have the same thing on both sides, but look on your formula sheet. Is there a formula that says sine 2x equals 2 sine x cos x? Down underneath tangent, there is, right? So to finish this, all we'd have to write is sine 2x equals sine 2x, because that's another formula on the, oops, sorry, 2x. Missed my 2 on this side. And we're done. Now, it might be worthwhile for us to write a few things in terms, if anyone's looking this over again, they go, wow, I got lost. I don't know what she did. Well, I can write little notes here and like this. Here I replace tan x with sine x over cos x. So if you're going back through, you can see that. Here I used that 1 plus tan squared x equals secant squared x. Then here I use, there's quite a few things we did here. Secant squared x equals 1 over cos squared x. That's another one. And then down at the very bottom, I use the idea that sine 2x is equal to 2 sine x cos x. This is good practice here, the stuff in red, to help yourself lead you through. You don't have to write it because I know all the identities and I can see whether you've subbed them in right. But that's a nice little summary of what we did there.